Yeah, go ahead. Okay, today we have Professor Jianbo Qi, who is an associate professor at Beijing Normal University. His research lies at the intersection of remote sensing and computer graphics, with a primary focus on 3D radiative transfer modeling of complex land surfaces and LiDAR point cloud processing. So, Jianbo is the lead developer of the LiDAR, which is a very well-known 3D RTM. So, Jianbo, the floor is yours.
Hey, thank you. Thank you for your introduction. So maybe I begin to do my talk. It's very happy to have a chance to talk with all of you online. It is currently uh, New Year in China, so we are in uh, a Spring Festival. Uh, Maybe just say Happy New Year to all of you. Today I will share some of my work in recent years about three-dimensional radiative transfer modeling of heterogeneous vegetation canopies. This is, I think, a bit not long story because I have developed this model more than 10 years. 10 years ago, I started to work on this model, uh, and now it has been, I think, a relatively mature model, and has been used in many researches. Maybe today I just briefly introduce fundamentals. That means why I developed such a model, and then I will introduce the less itself. After maybe I present some applications, some typical applications. Uh, so, uh, to begin, we know that vegetation is very important, and remote sensing now is only ways for large-scale monitoring. So we can use the reflected spectra of each pixel to do, for example, land cover classification. This is a very typical application of remote sensing. In quantitative remote sensing, we are more focused on the quantitative parameters for each pixel on the land surface. For example, the leaf area index. So it is important to understand the relationship between the uh, remote sensing observation and the vegetation parameters. So this is not an easy task, but you can also use observations to do the correlation. We can use some learning models, statistical method to learn the patterns from a large amount of large amount of observational data. However, this kind of method is not universally applicable. If we have a theory model, that is to derive patterns from the theoretical analysis, that means we can develop a theory which can be applied to any pixel of the world. This is called radiative transfer modeling in remote sensing. This is a general formulation of how radiative transfer model works. Usually, we take the component spectra, the landscape structure, and additionally the observational and illumination information as input. And then we use some solver, the radiative transfer solver, to compute the remote sensing signals, including the canopy reflectance, LiDAR, and chlorophyll fluorescence and photosynthesis. So this kind of information. So among all of these input parameters, landscape structure, I think is the most important one because it determines how we represent the real world and how the radiative transfer solver computes the remote sensing signals. There are many kinds of radiative transfer models. This is most famous one-dimensional model, such as the seal model, and also the geometric optical model, they abstract the trichromes into some simple geometry, like the inform model, this kind of analytical model. And in recent years, many researchers are focused on the three-dimensional model because it represents the world with very realistic structures. So this is also my research field. So there's some simple comparison between different kind of models. So if you want to develop a new model, so the first question I think we should consider is how to describe the three-dimensional canopy structures, and also based on these structures, how can we realize 3D radiative transfer simulations. So in last model, I think we use a very simple triangle mesh to represent the real world. For example, we can use a mesh to represent the complex forest. So this is a very common format. And also, we also use kind of turbid medium. This is a specialized representation in vegetation remote sensing because we assume the canopy elements such as leaves to be infinitely small, and then we describe as and we describe uh, their characteristic with some statistical parameters. So this is a very common approach, such as a dart model, flies model. This kind of model also use this approach. And also for the optical properties, we can use measurements, and or also we can use a leaf radiative transfer model like the prospect. So these are some common input. But for turbid media, this kind of things may be more complex. We need to use some advanced parameters such as extinction coefficient, single scattering albedo, and the scattering phase function to describe the optical properties of the turbid media. These three parameters are further linked with some structural parameters like the leaf area density, leaf angle distribution, and leaf scattering albedo, this kind of properties. Uh, so, uh, so we can use remote sensing signal to estimate, for example, leaf area density. So this is a basis for the radiative transfer modeling. And so for the radiative transfer solver, in recent years, I think retracing is one of the most popular one. So I start to use retracing 10 years ago to simulate 3D images from the 3D virtual scenes. So this is a very popular and a very common technique in computer graphics. And so my work just at the intersection area between computer graphics and remote sensing. In most cases, I use some theory, some method from the computer graphics to remote sensing field to solve some remote sensing problem. So this is a major technique I used. So here's an example. I think some of you are very familiar with this. This is a famous PBRT renderer. So this picture is not a real photo. It is just a rendering from the virtual 3D scenes. And also some video games can you still use ray tracing to simulate very realistic scenes to make the picture more beautiful and more realistic. This is why I want to develop such a model because we have seen the power of the retracing. They can compute very accurate physical information, especially the reflectance from the complex to 3D structures. So this is what remote sensing are trying to do. So I based on the ray tracing, I developed the last model, which can simulate hyperspectral and multispectral bidirectional reflectance, semi-infrared images, LiDAR signals. And also, in recent years, we have included the solar-induced fluorescence and the photosynthesis. We also provide a easy-to-use graphic user interface and the SDK for batch processing. So it is very convenient. It is very convenient to use these tools to create the 3D virtual scenes to do the simulation. And this is a very brief history of this model. We start from the 2013, and each 2 or 3 years, we will have some major improvement. And also, we provide a flexible plugin system, and now a lot of people are using our software, and they also contribute some plugins to help them or others to do the simulation or do some processing. So the the retracing is already a very widely used technique. In last model, we majorly use two kind of retracing algorithm. The first is a forward retracing. That means we send the rays from the light sources, and then we follow the propagation of the ray, and we record the intersection point, and also we compute the absorption, the scattering at the intersection and the intersections. And if we want to simulate images, so we usually use backward retracing. So we send the rays from the sensor itself, uh, and the rays that enter the sensor only are simulated. That means if the ray does not intersect with the sensors, they will not be simulated. So this can save a lot of time and improve the computational efficiency. So it is very suitable for simulating images. Also, we have included a new module in LAS to simulate the LiDAR pulse. That means we have modeled the propagation of LiDAR waveform. We modeled the intersection profile of the energy distribution and also its the time duration of each pulse. That means finally with this module we can simulate the LiDAR waveform, and if we perform the Gaussian decomposition, we can also output the LiDAR point cloud. So we also have provided a very easy to use graphic user interface to help users to do the simulation. This is a hyperspectral LiDAR waveform. So this is for SIF. We have included this leaf level SIF model, Prospect, as a basic leaf model in this module. And based on Prospect, we simulate the propagation and of the SIF signals within the complex canopies. And then we can simulate the remotely sensed SIF signal and also the total emitted SIF. So this can help researchers to investigate, for example, which angle of the observation will be better to estimate the total SIF of the canopy. These are some measurements comparison with some field measurements. We have used a tower-based SIF measurement system to verify our model. So we reconstruct the canopies with a terrestrial LiDAR point cloud, and we simulate the SIF. And also we compare the field measurements. So it shows quite a good consistency. And we we are also trying to integrate the 3D radiative transfer modeling with deep learning, especially to accelerate the 3D radiative transfer simulation. because we know that 1D model is usually very efficient, but they are less accurate, even for homogeneous canopies. 3D model are usually accurate, but they are less computational efficient. So we can combine the advantages of both models by using the deep learning. That means for the same uh, parameters, we perform the simulation with both 1D model and a 3D model, and then uh, we use the deep learning to learn uh, to uh, to learn the differences between the 3D output and the 1D output. That means we use deep learning to correct the results of 1D model. So after this correction, so uh, we don't need the 3D model again. We don't need it anymore. We don't need it anymore. We just use a 1D model and the deep learning to do the simulation. So this is will be much efficient, and also we have the the same accuracy with the 3D model. There are some. This is some our recent studies, and we have verified the results. It can be clear shows that with 3D model plus deep learning, we can produce nearly the same results with the 3D model itself. And also, uh, this is some this is some example directional reflectance, and we can this is some assessment of the accuracy of the model. We use RAMI. This is a very famous model intercomparison initiative, which has been started from 1999, and in the recent phase, there are many realistic canopies. So we attend this phase, and recently, the results has been published, and we can see that the accuracy of our model has been very good. Especially, it has been the reference benchmark. It is not worse than the last was among the models to set a reference benchmark. That means the accuracy of the model is quite, I think, is quite good. For the third part, I think I will introduce some applications of this model. The first case, so each case, I think will represent a research domain. For example, the most commonly used case is to validate some inversion algorithm. This example use less simulated FPAR and is corresponding reflectance to validate the coarse resolution inversion algorithm. For example, if you have developed a new inversion algorithm based on the model's reflectance, however, you do not have uh, or it is difficult to have field measurements, especially for the heterogeneous canopies, because each place maybe have different values, so it is difficult to do measurements. So if you have less model, you can construct a series of heterogeneous canopies with different leaf area index, and we can simulate the models like bidirectional reflectance factor, and you can input this reflectance to your inversion algorithm, and then you estimate a value here. So this is estimated value. However, let's also provide a ground truth value. So the simulated FPAR. So this is very accurate because we simulate the rays from the sun from the atmosphere within the canopy, and we record we record the absorption at each intersection point. So this is very accurate. Then you can compare these two values uh, to verify whether your algorithm is accurate or not. Uh, the advantage of this approach is that we do not have measurement error, so we can theoretically validate our inversion algorithm to see whether it is accurate or not. So this is a validation. So the second case is to use the 3D radiative transfer model to do some sensitivity analysis. So in this study, we use less model to assess the impact of soil anisotropic reflectance on the canopy reflectance. Uh, we know that the reflectance of the soil is not isotropic, so different directions may have different reflectance. So, and in which case, we can assume them as Lambertian surface, and in which case we cannot do the assumption. So if you do this in the field, it is very difficult and time consuming. So if we use a 3D model, we can do this task. I think within 1 hour you can finish this analysis. So in this study, we construct a series of canopies with different canopy fraction, and then we compare the total reflectance under the two different soil assumptions, and it can be apparent to see that when the canopy cover is higher, the difference between these two assumptions are minor. That means for dense canopies, we can ignore the anisotropic of the soil. We can assume them as Lambertian because of the multi-scattering between the soil and the canopy. So this reduced the effects of the anisotropic reflectance. So this is sensitivity analysis. I think another case is about the forestry study. Uh, that is to quantify light absorption of each individual tree. In some forestry research, they are very interested in uh, the light absorption by each individual tree or by a small forest plot. However, in the field, it is also very difficult to measure the light absorption because we do not have such a instrument currently. However, if we have less model, we can do this with simulation. That means we use the LiDAR data. For example, the terrestrial LiDAR or UAV LiDAR. We can reconstruct the forest plot with very high precision, and then based on this 3D landscape. So this is an example of the reconstruction. We use terrestrial LiDAR to reconstruct such a forest plot. And based on this reconstruction, we can use lights to compute or to simulate the light absorption for each individual tree. And also we can provide the height profile of the absorption. That means we have more insight view of the light absorption to help you to do research regarding light absorption and study some ecological process. And also we can provide the light availability of the underground using less model to see how much light has been blocked by the up layer and how much light is still available for the underground. So another case is about using LES to in deep learning, especially for tree segmentation from the satellite images. Uh, we have known that if we want to do segmentation using deep learning, usually we need the label of the tree chromes. We should do it manually. However, this task is also time consuming. So if we have a virtual landscape, we know the true boundary of each tree chrome. So this is the label. It can be automatically generated from the virtual scene. And also, based on the virtual scene, we can simulate the satellite images. After the simulation, we have the synthesized satellite images and the corresponding automatically generated labels. So we can use this directly to train our deep learning model. To do the segmentation, we have verified this approach with manually labels. So it can be seen that the synthetic 100 percentage, that means we use 100 percentage automatically generated labels. So it shows a very comparable accuracy with real manually labeled images. So that means using the synthesized images to train deep learning. Uh, I think it can save a lot of time. We can also do some mixture. That means we use all of the sensitive images with a small part of the manually labeled images. So this will increase the accuracy. Uh, so uh, this is a combination use of 3D model and deep learning. So the next case is we can use the 3D virtual simulation to evaluate some new instruments. For example, the hyperspectral LiDAR for forest disease detection. We know that hyperspectral LiDAR is not mature currently. We do not have a very lightweight, uh, very applicable instrument. However, if we want to evaluate uh, its efficiency for the forest disease detection, we can only use simulation. So in this study, we use reconstruct the virtual scenes, and based on this virtual scenes, we constructed a series of different scenarios. Each scenario represents different kinds of forest disease. And we, based on all of these scenarios, we can simulate hyperspectral images and also the hyperspectral LiDAR. Because hyperspectral LiDAR has a 3D structure, we can divide it into different layers, and each point have have different have a reflectance spectra. So we can construct some vegetation indices to verify uh, how they can distinguish different kind of forest damage. So from the results, we can see that the hyperspectral images, I think, is not sensitive to some forest damage, but for hyperspectral instrument, it is very easier to distinguish them. Also, we can provide some advice how how to choose the wavelengths for the hyperspectral LiDAR instrument. For example, maybe we can use only five wavelengths is enough for some applications. If we use this kind of simulation, so it will reduce a lot of time to do the real experiment. And the the next case uh, is about the inversion. This is for leaf chlorophyll content estimation. So before if we want to do the uh, leaf parameters estimation, Usually we will use a cell model, per cell model, or info model. This kind of analytical model to do a lot of simulation to train a inversion model such as neural network or the random forest. But if we have a 3D model, we can have more realistic input structures. So we use the LiDAR data to reconstruct the realistic canopies. And then, based on these canopies, we use less model to do a lot of simulation. And then we have a simulation database. Using this database, we can train the estimation model. Here we use deep learning model, and then we can use this deep learning model to do the estimation. Uh, Here are some results. Using a 3D model, we can see the accuracy is much better than the traditional Percel because the Percel model do not consider the heterogeneity of the canopies. And using 3D model, we can even reduce the pixels. If we use UAV images, this kind of very high resolution images, we can even remove the shaded pixels. That means this kind of black pixels because they do not provide the real information of the uh, of the leaves. So we can remove them and we use only the sunlit pixels to do the estimation. So this will improve the accuracy, especially for the very high resolution UAV images. So I think this is the advantage of 3D model because we can consider the specific structures of each forest plot if you have LiDAR data. And we can also train a model, and this model can be applied to large scale. For example, the entire United States and the entire China with the Google Earth engine. So we applied this model on the Google Earth engine, and we can use this model to do the leaf chlorophyll content estimation for a very large scale. And for so this is a case that from a user they use a less model to do the leaf area index retrieval of grassland. Traditionally, we use Percel model uh, to do parameter estimation for grassland because we think grassland are usually homogeneous canopies. However, if you look at the grassland, you will see that uh, most grassland have a very heterogeneous structures because the soil the canopy fraction is usually not very high. We want to represent this real structure, and we first construct a lot of grass, and then we use this grass to do some simulation. So with different leaf area index, and we use this to simulate a reflectance database. After the simulation, we can use this to train estimation model and to do the inversion. And also we compared this approach with traditional Percel model, and it can be apparently observed that for training phase, Percel model will be saturated. So especially when leaf area index is larger than 4, but for 3D model, so this saturation is not very apparent. So we also verified this estimation with real measurements. It can be seen that if we use a 3D model, less trained model, so this accuracy will be much better. So this estimation can also be applied to orchards. So in orchards, we know that the canopy structure is usually complex and the tree are usually isolated. So if we want to do the inversion for each individual tree, for example, to monitor the leaf chlorophyll content of each individual tree, uh, usually we should use 3D model because 3D model can consider the heterogeneous structures among the trees. So we use less model in this study to construct a lookup table. And with this lookup table, we can estimate the leaf chlorophyll content for each individual tree. And so I think this is very useful in agricultural industry. So the next one I think is about the photosynthesis of heterogeneous canopies. So in I think in the last year, we have introduced a new modular units to do the photosynthesis simulation. Because we can simulate a very accurate APAR for each individual leaf, and based on this information, we combine the leaf photosynthesis model, the Farquhar model, and we can estimate the photosynthesis rate for each individual leaf if we provide, for example, the solar radiation information. So this is a new modular inlet. I will take some example. With this new modular, we can simulate the photosynthesis rate for each individual tree or sub-tree or sub-canopy is also possible. So we first use some LiDAR data to do reconstruction. So all these things are from the UAV LiDAR and uh, the terrestrial LiDAR, and we reconstruct this kind of canopies from the point cloud. And then we input these virtual scenes into less model, and then we can simulate the sub canopy photosynthesis rates for each tree clone. So from the morning to the afternoon, and this is a dynamic of the photosynthesis rate. So I think this is very useful for some ecological studies if we want to study the relationship between the canopy structures and the photosynthesis. Uh, so uh, Maybe just conclude my talk. So I think even in recent years, deep learning is becoming more and more popular. But I believe that radiative transfer model are still essential, are still important, need to be improved to understand the interaction between solar radiation and the vegetation canopies. So I think this provide another approach, except for deep learning, to help us to explain, to estimate the inversion process. So I think our team are still important. And the 3D model, such as RLS model and also the DART model, uh, an advantage of them is that they can support very complex canopies. They can represent very realistic canopies. It provides more functionalities than traditional 1D models. So we can use this kind of models to do some more advanced studies. So I think this is why we are still trying to improve the 3D radiative transfer modeling. So this is all my talk. Thank you very much.
Thank you. Very impressive work. Any questions? Where you start here behind or?
Thank you very much, Jimbo, for your talk. I agree with you that I think combining physics with AI would be the next hot topic, hopefully, in
Yeah,
the
yeah.
future. I have a question. I saw you presented a case study about the chlorophyll map of the whole United States or whole China. I wonder how you simulated such a big database, because you mentioned that 3D RTM is quite slow in doing data simulation, and you typically fix the 3D scene. How would you generate such a big database to do the inversion for the whole country?
Okay, so this is a very, I think, a very important question. This also the I think for 3D model, it's really difficult. Uh, However, in this work, we do not do the simulation for each pixel of the entire United States or entire China. We just choose some typical landscape. So we use all the uh, LiDAR point cloud we collected especially from the new sites in the United States and also some LiDAR point cloud in China. And we choose a lot of forest plots, randomly choose a lot of forest plots from this LiDAR point cloud. And then we do some, for example, uh, the classification, the KNN, the key nearest neighbor algorithm to do the clustering. And then for each cluster, we choose some typical point cloud. So in this way, we think we choose a city of point cloud which are representative for a lot of landscape. And then based on this point cloud, we reconstruct the 3D scenes and do the simulation. And then we construct a training database to train a inversion model. So it is not for each pixel, it is just some representative forest plots in this study.
And for a follow-up question, for the simulation, do you have the independent sampling of each variable across the whole range and then have the random combination of every possible combination of the variable values?
You mean to the simulation with less?
Yes, yeah. When you sample the value from of each variable from their value range.
Uh, in that simulation, we do all the possible combinations.
Hmm.
So it is a very large database.
Mm.
Thank you. Back to you.
Yeah. I just want to say like one of the work that you show is actually very similar to one of our papers. It's I think this is like you're using GAN to generate some like pseudo labels. It's actually not pseudo labels, so some ground truth labels, then you use it for segmentation. Actually, we have a very similar work here that we are using like a game engine. It's called Unreal Game Engine. And we use Unreal Engine to simulate to create some like virtual game things, and then we collect the data from that game things. And also each picture will have its corresponding, like masks. And then we'll also use it to train the model and also mix this like pseudo labels with the real labels and see how it performs. So I think, yeah, it's very, very similar.
Yeah. But if you use game engine, I think a problem is the texture. I don't know if they are very similar with the uh, real images. So here in my study, you can see that the texture of the ground are very uniform. Is if you only use less model, if you only assign the very simple ground reflectance, so that's why we use GAN to learn the texture from
Hmm.
the water view images to make them very similar. I think game engine is also very good approach. I think maybe better if you have a lot of samples, a lot of landscape. But
Hmm.
I do not try the game engine. It is a bit complex.
Right. I think the advantage of a game engine is that they do ray tracing very efficiently, and they also use support from GPUs to do the ray tracing, so it makes it much more efficient compared to
Yeah,
traditional.
yeah, yeah.
Yeah.
Yeah, I agree.
Emily, her question. Go ahead.
Hello. Hi. Thank you so much for your talk. I really enjoyed it. We use I've been using radiative transfer models for a long time, and we're playing around with TLS now in our group with Anne, who's on the call, using the DART model. And I wanted, I'm interested, but not currently using simulated data, and I'm curious about this idea of realism. You know, you mentioned a few times it looks realistic. We said it's kind of pretty, and I wondered how you define realistic with these simulated data. And then as a sort of second or like slightly follow-up question, I'm interested in realistic representation for things like photosynthesis modeling and thinking about things like variability of chlorophyll or nitrogen through the canopy, and also things like leaf angle variability, which can obviously have a huge effect on the BRDF or the reflectance, that changes through the day and through the year and depending on the weather. And I wondered how flexible your model is for including that kind of ecological realism.
Yes, thank you. Thank you. So you also pointed out a very important question for using 3D model. So in my opinion, how to define the realistic
I think we may have lost the speaker for a minute.
Yeah. It happens because I assume that he's in China, so he have to use a VPN
The
to
VPN.
join this Zoom.
Right. Oh, I see. Oh,
Yeah.
Zoom is not so good. Okay.
Yeah.
Yeah, but I think, I mean, sorry. Jelba, can you hear us?
I can send a text message.
Can you do that, please?
Yes, you can't hear you now.
Let me just pause the recording.
laptop. Okay, just I share the screen again.
Yes, no problem.
So I don't know where I just talked. I just see that for realistic, in my view, I think it is not a realistic. That means we just compare our model with traditional, for example, the cell model, abstract the trichromes into homogeneous layers, and the info model, abstract the trichromes with ellipsoid. So our realistic means that we have more detailed structures. I think 2 years ago I have a study. I just verified which detailed information can influence the reflectance. I find that usually we do not need very, very detailed. Maybe we do not need the information of each individual tree. For some applications like the Sentinel resolution, 10-meter resolution, we use maybe abstract trichromes, use alpha shift, maybe it's better. I think it's enough maybe to produce accurate reflectance. So that means realistic. It depends on the resolution, which resolution you are working on. Maybe 10 meter, 5 meter, 2 meter, maybe they are different. So for some real applications, we found that the leaf, maybe the leaf chlorophyll content may be different for each individual leaves. So for this case, I think it's difficult to obtain the information. Usually, I think we consider the vertical profile. I think is enough for many applications. So maybe this is my point of view about this. I don't know if I answer your question. If I correctly understand your question.
No, yeah, it's
Thank you.
interesting to think about. Sometimes I wonder if you can also introduce sort of optimization ideas in. So, you know, leaf nitrogen optimally distributed, so not necessarily just vertical, but sort of in the sunlit to shaded profile, that if a tree has only a certain amount of the nutrient available, it's likely to put it into the sunlit leaves to maximize photosynthesis. I don't know.
Yeah. Maybe it's
Thank
not
you.
only vertical.
Clement, please go ahead.
Yeah, first, big thank you for your nice presentation and this very good work. I really like it. What I like most is, let's say, the ability to simulate across, let's say, sensor modalities, reference data, right? Because as you have shown, right, you cover from thermal infrared, fluorescence, LiDAR, full waveform. Probably you can also do point clouds and hyperspectral reflectance. Probably you can do all except perhaps microwaves right now. So this is very, very useful. But obviously, as Emily pointed out, and as we have already discussed, right, to what extent can you, let's say, in the forward mode, when you simulate your scenes or your pixel signatures, if you like, how realistic can you do it? Because I can imagine that, let's say, the structural information, the purely structural information, you can indeed get from terrestrial laser scanning or from UAV, RLS systems. But then when it comes to the distribution, especially the vertical distribution, and perhaps, Emily, you meant this also vertical, and then in the tree crown, depending on the shading, how well can you really describe the distribution, for example, of pigments in the tree crown, right? And how realistic is then your database that you use then to learn a kind of transfer function then back from the signatures to your variables that you're interested in. So this is something where I think, and again, perhaps this is what Emily perhaps meant, if you are able to simulate and to trace what is absorbed, which photons are absorbed by bark and wood, and which are absorbed by leaves, I think the plant in itself optimizes the allocation of pigments depending on how much light is in the canopy. So my advice would be to look at this feedback, right? To look, I hope it's clear. If there's less light, the plant has no reason to invest a lot of energy to get the pigments there. So, and this gives you a means perhaps to better describe the pigment concentration and variations inside the canopy.
Yeah. That's maybe a solution. I know that for our model, I think, as you have mentioned, it is more about structural information, because we use LiDAR as kind of to reconstruct the structure. But for the pigment, for the leaf chlorophyll content, I think the difficulty is not limited by the model, because we can simulate the landscape with each individual leaf has different pigment. So the model has the ability to do this kind of simulation. But the difficulty is, how can we obtain the distribution of the pigment? So it is very, very difficult, I think, currently. We have LiDAR, we can measurement the structural information, but the pigment information, we cannot do this kind of measurement. So I think this is difficult. However, if maybe in the future, and we are trying to use the lights to do the photosynthesis, I think the pigment distribution may be related to the light availability within the canopy. There is a model, I think, in the ecological research area, P model. P model. This model is to explain the pigment, for example, the VC max, this kind of parameters, how they are related to the average light absorption. So maybe with this kind of theory, we can maybe in the future to integrate this with a radiative transfer model to better to do better simulation, and especially for more realistic, I think.
Yeah, Clement, does that
Thanks.
make sense? Yeah. Maybe if I can ask the last question, we do need to end in a minute. The way I see it is at an abstract level. I think what the other questioners have also pointed out is that the model, which was the millions of leaves and bark and trunks and soil, many parameters. Let's say order of million parameters, and the output is one parameter, LAI or whatever it is, right? So we're going from a very large parameter space to just a single scalar value. And in between, we have a complex simulator, which is essentially translating from the millions of parameters down to just one value, which leads to the obvious question that many of these parameters are chosen perhaps arbitrarily or based on guesses, or we don't know the actual distribution of leaf angles over a landscape, for example. So we get a kind of distribution, we have some guesses and so on. And so the task becomes saying, if I make this guess for what the landscape is looking like at this detail level for these parameter values, I get this output value, and that seems to match reality, and therefore my model is good. But I could have had a different distribution, which was quite unnatural, quite bad, and would also, for whatever reason, give me a similar output value. So we have in some sense, a very under-constrained system. And so the worry is that we cannot infer the correctness of the model based on this because there are too many parameters.
Yeah. Because this is an underdetermined system.
Yes.
I think using 3D model can only solve a small part of this problem. Maybe we need more observation from different aspects, from different instruments, to reduce the number of parameters. Maybe in the future, I think.
Yeah, I mean, obviously, what you've done is very interesting and useful work. I was just pointing out this inherent problem in this line of work, no matter who does it, whether we do it or you do, which is that we're going from a very large number of parameters to few parameters, and we need to be careful to be caveating that, saying that this is not necessarily the ground truth, because we don't know the ground truth. We don't know the pigment distribution. We don't know the exact structural properties down to, I mean, maybe you get to centimeter level, but maybe the leaf angles, we don't know exactly. If the wind blows, the leaf angles change. Okay. So, I mean, obviously that changes what you're seeing from a LiDAR or from a satellite. So we have to be careful of all of those things. But anyway, that's more of a philosophical point. And, I guess we are all on the same page with regard to that. So let me end by thanking you very much. I think it was a wonderful presentation. Thank you all for coming, and we will continue with our next presentation. Actually, next week we have Yifan Ban from KTH talking about the Pangea Foundation model.
Thank you.
So yeah. Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you.
Thanks.